welcome to this lecture. We are going to talk about the plate fin type heat exchanger, where it will be handling multiple streams, multiple fluid streams. So, while talking about the plate fin heat exchanger characteristics, we have told you that one of the characteristic features of the plate fin type heat exchangers is that it can handle multiple fluid streams in a single unit, and that we take it as an advantage because several fluid streams in a single unit can often offer high degree of compactness and also a thermal performance enhancement in the thermal performance. So, if we look at the plate fin type heat exchanger geometry to accommodate multiple fluid streams in a single unit, how it has to be done. So far we have talked about the two fluid stream geometry. Just if we enhance another fluid stream for ease of understanding, we have here shown only three fluid streams. So, here one of the fluid stream is fluid number 1, fluid 1. So, it is entering at this layer. So, at this side, and it is moving out from this side. So, as you can understand that this is the fluid stream entering from this opening, and so many others, which are in this layer, particular layer, it will be coming out from this end, and finally it will move out from this side. Now, what is about the other fluid streams? Say fluid stream 2, this is entering from this end, and you can understand that this is in layer 2. So, it will be coming in from this side, and this side. So, here this layer is for designated for fluid stream 2, this is for fluid stream 2, this is fluid stream 2, like that, and they are all coming out on this side. So, what is about the third one? The third fluid stream. So, it is entering from this side and coming in. So, this is occupying the first layer and then moving out from this side, and finally it is going out from this header. So, like that, the arrangement is 3, 2, 1, and there is a repetition of this again 3, 2, 1, and so on. So, it is like that it will be arranged. So, if we look at the geometry, particular geometry of this particular heat exchanger, and if we restrict ourselves from this length to this length, we find that these three fluid streams are, this is the fluid stream 3 is entering from this side, and this is moving out from this side, whereas the very next fluid 2, which is entering from this side and moving out from this side. So, they are in counter current configuration. So, if this fluid 3 is entering from this end and the fluid 2 is entering from this end, so they are in counter current configuration within this span of the exchanger. What is about the fluid stream 1? Now, here the fluid stream 1, we find that it is, though it is as if look like a cross flow arrangement, but immediately after going inside it will take a turn, and finally it will move out from this side. What is about the fluid 2? In contrast to the fluid 2, the fluid 2 is moving from this end to that end. The fluid number 1 is entering from this end to this side, and so that means this is also in counter current to this. So, we can see that this fluid stream 1, 2, 3 are in counter current configuration with each other. So, again the 3 will coming here and 3 will come from this side, it will come out from this end, and 2 will be coming from this end to this end, and so on. So, all these 3 fluid streams are in counter current arrangement to each other, whereas it will be overall it may look though in a counter current and cross flow arrangement, but internally within this length they are in counter current configuration. So, this is one of the beauty of this plate fin type heat exchanger, where it can handle multiple fluid streams, and not only that, these fluid streams can be I mean as many as 11 number in I mean we have come across heat exchangers handling 11 number of fluid streams. And another particular feature of this particular type of heat exchanger is that we may take out the fluid at some intermediate points. That means intermediate entry and intermediate exit is also possible. Intermediate entry of the fluid stream and intermediate exit of the fluid stream, intermediate exit of the fluid stream is possible. That means it need not necessarily enter from this end and come out from this entire, I mean travel all the way to this heat exchanger length and come out from this end. If someone wants, it may be taken out from this point also, and it may so happen, depending on the heat exchanger length, we may think of entering the fluid stream from this end. So, this becomes intermediate entry and this becomes intermediate exit, and that is possible for any fluid stream. So, this intermediate entry and exit of this multiple fluid stream is again another characteristic features of the plate fin type heat exchangers. So, with this basic knowledge of the fluid streams, now we go to the next picture, where we can see some of the plate fin type heat exchanger. This has been taken from the Alpema heat exchanger, and here we find that this particular exchanger is showing as many as 5 fluid streams, and many of them are entering. This is particularly is entering from this end. So, this is one end, and here you may find that this is something where there is an intermediate entry or exit, and this is the fluid stream 4 outlet, fluid stream 2 outlet, this is stream 2 inlet, and this is where the fluid 4 is moving out. Stream 1, this is stream 5 outlet, it is not shown the entry, showing the entry of the other streams. So, which must be located on this side or this side somehow. So, this is a typical type of plate fin type heat exchanger, and you can understand that it should have a very good type of distributor fin before it comes to the main length of the exchanger. So, in this type of exchangers, it is the parallel, counter as well as cross flow arrangement is likely between the fluid streams. So, it will depend on the optimum fluid pattern. We will talk about that as you can understand that when we have say A, B, C fluids or A, B, C, D, E number of fluid streams, then how do we arrange them? That also makes some kind of possible configurations, like whether we should go for A, C, B, E, D like that, this combination, or we will arrange them in a different combination, and how this pattern will, the layer stacking pattern, we will discuss about that part sometime later. So, when we talk about this kind of plate fin type exchangers, now imagine that the configuration of the heat exchanger is already known or it's basically we are not going to talk about the design at this moment. We are going to talk about the simulation process of the heat exchanger or multi-stream plate fin heat exchanger. That means we know about the total dimensions or the configuration of the heat exchanger, and we know the inlet fluid stream conditions. So that we have to find out the performance of this plate fin type heat exchangers, or we will try to find out what are the exit fluid streams temperature and the pressure. So, how to do that? We will try to understand that one and the associated problem with this particular type of heat exchangers. So, we will look into that. So, now imagine that this particular example we will be showing you to demonstrate why this design or simulation particularly is complicated in case of plate fin type heat exchanger. Imagine that we have a fluid stream which is all the fluid streams are entering from say this end to this end. They are entering from this side and moving out from the other side, except one fluid stream. But let us this is where we have these three fluid streams. They are in parallel combination to each other, but these two fluid streams are in counter current configuration, or it may be of a different configuration also. It may so happen that the fluid stream 1 is entering from this side, say another fluid stream that fourth earlier which was there at this location. Now, we have this on this side and this is the other. So, this is fluid stream 1, this is 2, sorry, this was 4, right, this is 2 and 3. So, 1, 2, 3 are entering from this end and the other one is entering from this end. So, one of them is in counter current to the other. So, this is one combination. It could have been such that all four of them all the four fluid streams are entering from one end. So, simulation of this particular type is bit easier as compared to the other situations we have talked about so far. So, here all the fluid streams are entering from one end and we need to find out the exit temperature or the exit pressure at this end where it is not known. And what we do is that we go step by step. If we divide this entire exchanger into small piece, and what we try is if it is divided into a very small piece, and we can try to find out the exit temperature at this point. So, we know all this temperature at this end, it is known at this face, and we can try to find out the temperature at this location. So, if we can find out the temperature at this location, so it will act as an input for the next section, and we will be able to calculate the exit temperature for this tiny length of the exchanger. So, it will keep on integrating from this length to this direction, from x equals to 0 to x equals to L, and we would be able to finally get an exit temperature at this end. So, that is what is the process when all the fluid streams are entering from one end and moving out to the other side. So, all the fluid streams are in parallel combination to each other. But if the situation is not that, if three of them are entering from one side at least, and one of them is coming from the other side. So, if this is the situation, then what happens? So, we can make an estimate of say these three, because here at this point if we have to make a small section of this exchanger, what we need, maybe we will be starting from this end, and where all these three fluid streams are temperature, fluid stream temperatures are known, and so we have it is convenient to start from this end if we just assume only one fluid stream temperature for this one, so we should have been, I mean, we should be ideally able to predict the outlet temperature for this 3 fluid stream, and then one fluid stream on this side. So, what is the problem if we have this kind of situation? This can also be handled if we write the governing heat transfer and pressure of equations, and then you try to solve it step by step from this end to this end, just by making an assumption for a single fluid stream. So far as the assumption is associated with a single fluid stream, we have no problem. So, but if it is such that if we have to, if the configuration is such that we have more than one fluid stream entering from both the ends, I mean, this is like we have a counter current fluid stream arrangement where alternative hot and cold fluid is there, like this is fluid stream 1, this is fluid stream 2, fluid stream 3 and fluid stream 4. This is 1 and 2 are in counter current, 2 and 3 again are in counter current arrangement, as well as 3, 4 are again flowing counter current to counter current arrangement. So, now in this configuration what happens is that this has been shown by Hessler in her paper, the performance calculation methods for multistream plate fin type heat exchangers. Here what she has shown that when we this is a configuration where we have, like, let us look into this carefully. So, when this is calculated from end A, that means, as we were telling you, that we have 3 fluid streams here. You see 2, 3, 4, they are entering from one end, and that end has been designated as A, and the other end is designated as B, and from B end, which is the fluid flowing, this is the fluid number 1 that is flowing from end B to end A. So, this is end A, this is fluid stream number 1. So, now when they have calculation started from end A, that means they have made an assumption about this exit temperature, and they have approached the solution from end A to end B. Then they are finding a convergence of these outlet fluid temperatures. But look at the situation when they have started from the end B. End B means, what are the things that he have to she has to do is that they are coming like this. So, if we have to simulate from this end, so one has to assume the fluid temperatures at these 3 points. So, even if someone is very close to the actual exit temperatures, and if someone try to start simulation from end B, it will be such that it will very soon it will diverge, the solution will diverge. So, we are not going to get any kind of solution when we are going to make a very even if we make a very close assumption to the exit temperature also, it is not going to converge. So, in order to solve this problem, this iterative scheme is not going to help much. So, we need to adopt a different type of scheme for the multiple fluid stream heat exchangers, and there are several works. One of them is of course by Hessler, Herschel, and there are other papers or literatures available in this in different journals and books. So, we will look into that. How do we go or about it? So, we will try to first solve. We will go to the If we now look that we have different fluid streams like this, say A, B, C, D, this is fluid stream A, then fluid stream B and C and D, and they are arranged in either a parallel or counter current combination. So, first of all, what we need to find out is how is the governing heat transfer equations, and then only we will be able to find out the solution of those governing heat transfer equations. So, now what we need to solve these equations, what we have with us is the heat exchanger geometry known to us, and what is known is the inlet temperature of all these fluid streams. This is fluid stream B, this is fluid stream C, inlet is known, and this is fluid stream D, inlet is known. All the inlet temperature and the heat exchanger configuration is known to us. Now, based on this, we should be able to find out the exit temperature of all these fluid streams. So, A, B, C, D exit temperatures. So, if there are 4 fluid streams, we need 4 exit temperatures. Then, what are other things that are not known are the wall temperatures, say TW0, if we designate it, then TW1, TW2, TW3, all these wall temperature also it matters. So, we have then n number of fluids, then we have n plus 1 number of wall temperatures are known to us. So, we have n number of fluid stream and their exit temperatures are not known, and we do not have information about the wall temperatures for the n plus 1 number of separating plates. So, altogether what we expect that 2n plus 1 number of unknowns, we look for the solution of that 2n plus 1 number of unknowns. Now, if we have to look for 2n plus 1 number of unknowns, we need 2n plus 1 number of equations. So, we have to construct equations for 2n plus 1 number of things. Now, as you can understand that if we make a cross section of this plate fin type exchangers, we will find that there are fins in between the two layers, and it will be looking like this. So, what we will try to do is that we will try to solve what we will need is basically a kind of energy balance for all the fluid streams, and particularly the fluid streams all the fluid wall temperatures. So, it is all the fluid streams. What we can write is that we also know the mass flow rate for the individual streams. So, M A dot, M B dot, like that, all the mass flow rate of the fluid streams are also known to us. So, if we assume that for these equations, we should be able to write in terms of m dot A, C P A, and then delta T A, where one of the temperature is known, the inlet temperature is known, but the exit temperature is not known. Similarly, we would be able to write C P D, and then we have the delta T and delta T D, and there also we find that one of the temperature is known in the delta T, inlet temperature is known, but the exit temperature is not known. Now, that is about the energy balance. For a particular channel, if we have this kind of channel, and we will try to estimate what is the total heat that is getting transferred when it is the fluid is flowing from this end to this end, and say if it is some fluid 1, and it may be depending on its surrounding fluid, it is having some other fluid on this side, and it may be for the terminal fluid it is then I mean end cap would be there for the terminal fluid, and on this side there will be another fluid, say fluid 1, if it is fluid 2 will be on this side. So, it will have interaction I mean depending on the temperature difference, either this fluid will give heat or it will receive heat. And when we have fluid stream I mean and it is having some adjacent fluid stream, and if it is cold or hot, then it will decide I mean whether it has to give heat or it has to pick up heat. So, like this either it may give heat or it may have to give heat to this depending on the situation or the fluid's temperatures, or the situation may be such that it is receiving heat and also receiving it from the bottom fluid. So, there are different I mean configuration that is possible, and the simulation has to take account of that situation. So, basically what we need is a Finn equation. If you remember that in the last class we have in one of the earlier classes we have tried to solve the Finn equation, where the Finn is connected between two surfaces or confined between two surfaces, say T A and T B, and we tried to find out a solution T A and T B, and they are connected by a thin pin, and we tried to find a solution for this one, and there we have been able to find out the temperature profile for that fin, and that was theta x, given by theta x, and theta x was obtained as theta a multiplied by 1 minus omega and e to the power m x plus omega into e to the power minus m x, and this is all, this one is multiplied by this, and where omega is equals to e to the power m l minus r, where this L is the length of this fin, and this is in the denominator we have sine hyperbolic m l, and but r is just nothing but theta b by theta a. So, this has been derived from or taken from the paper by B S V Prashad and PRASAD, and we have, it has been published in the journal of International Journal of Heat and Mass Transfer, volume 39, issue 2, and the pages are 419 to 428 of 1996. So, if any one of you have to go through it, you can critically look into this paper, where you will get this analysis, and not only that, you can also look into the book we have referred, that is by Shah and Shekulik. There also you will find this analysis available. So, now based on this Finn equation, we know the Finn temperature profile or the temperature profile that is existing in this fin connecting between the two surfaces. Now, once we have the knowledge of this fin temperature profile, we would be able to calculate many things, which we will discuss in the some of the next classes. Thank you for your attention.